Hello everyone, this is Doc Fan. Today let's discuss a very interesting question. How can a rope of mass m actually weighs 3 mg on a scale? This is a very interesting question related to momentum. And after today's discussion, you should have a very good understanding about momentum and continuous mass. Let's discuss it today. So let's frame the question like this. Let's say a rope of mass m and length L is hanging vertically with one end just in contact with the weighing scale and the other end holding by hand. This is our experimental setup. The question asks, after releasing the rope, what is the maximum weight read by the scale? We know the weight shown by the scale actually equals to the normal force provided by the scale. So this question basically asks, what is the normal force from the scale? We know after we release the rope, more and more rope will fall on the scale. So the weight seems to increase all the time. Let's draw a schematic to demonstrate the process. Let's say this is our scale and this is our rope right before our release. Then after we release our rope, we know this is something that happened. Some of the rope actually falls onto the scale. If we say the rope falls by a distance of x, then the part on the scale would have a length of x. The normal force on the scale would definitely support this part of the mass. So we can say that the normal force equals to the weight of the rope, but there is something else. What is the other part of the normal force? We realize after we release the rope actually have a downward velocity. But when the rope is in contact with the scale, the rope actually stops. So the rope has a velocity of v, then its velocity becomes 0 after impact with the scale. So clearly, scale provides another force which stops the motion of the rope. Then how do we use this velocity change to find the force due to impact? An equation naturally comes to our mind, that is delta P equals to the net force times the time. Because we know the momentum of the rope changes when it is collided with the scale, then we know there should be a force from the scale to the rope. And if we pay attention, we notice only the small part of the mass that is in contact with the scale actually experience this deceleration. So if we assume in a very short amount of time, if we assume in delta t, the small mass that actually in contact with the scale has a mass of delta m. We know its initial velocity is v, and we know its final velocity is 0. Then we can find its change of momentum. If we consider going up as positive, then the initial velocity should be minus v. Then let's write down the change of momentum. The change of momentum delta p equals to the final momentum minus the initial momentum. The final velocity is 0, so the final momentum is 0. Then minus the initial momentum. The initial velocity is minus v, so the initial momentum is minus delta m times minus v. As a result, the change of linear momentum is delta m times v. Then how about the impulse? We know for this small mass there should be two forces on it. One force is its gravity, F2 going down. The other force is the force from the scale. Let's call it F. So the impulse would equals to F minus Fg, then times delta t. So we do not know F, but we do know the weight for this small mass, which is in contact with the skew, should be minus delta m times g, then times delta t. And on the left, we have our momentum. On the right, we have our impulse. If we simplify this equation, we get delta mv equals to F times delta t minus delta mg times delta t. We know this term right here, delta m times delta t, it's a higher order small value, so we can ignore this value here. So then we get F times delta t would equals to delta m times v. As a result, we can get our force equals to delta m divided by delta t times v. So this is our impact force. So this force right here, which is our impact force. Now we know the two contributions for the normal force on the skew. Part of the supporting force is used to support the part of rope on the skew. The other part is being used to stop the rope. Now, what is this weight and what is this impact force in detail? We know the total mass of the rope is m, and we know the length of the rope is L. Then we can define something called linear density, which is mass divided by L, which shows our mass per unit length. Then this weight right here can be written as m divided by L, our unit length, times the distance of the rope on the skew, which is x, then times g. So that is the weight for the rope that is on the skew. And then how about this impact force? This impact force, we got it right here, which is delta m over delta t times v. Because we have defined the linear density, we know this delta m can be expressed as delta x times linear density. So the longer the rope, the larger the mass, right? So this equation then can be written as x times mg divided by L plus delta x over delta t times lambda, which is mass over length, then times velocity. Then if we pay attention to this right here, delta x over delta t, that is the velocity of the falling rope. Then this equation can be written as x times mg divided by L plus mv squared divided by L. Everything here is known except the velocity. Then what is the velocity here? We know for the rope, it is falling, right? But what is the velocity of the rope? One thing that is very important here is rope only provides tension. Rope can never have compression. So for the rope above the skew, it is going through free falling. Why? Even though the skew gives a supporting force onto the part of the rope that is in contact with the skew, but that compression force or that normal force cannot be transmitted to the rope that is above the skew. So the rope above the skew is always experiencing free falling. And we know from the starting to the moment the rope falls by x. By kinematics, we know that velocity equals to root of 2gx. So we actually know this velocity right here. If we substitute this velocity into this equation, we should get x times mg divided by L plus m divided by L times 2gx. If we now combine these two terms, we should have 3x times mg divided by L. And that is the normal force from my skew. And that is the weight read by the skew. As you can see, the mass and L is a constant. So this normal force, or the number on the scale, is only determined by how much my rope has fallen. That is X. And this question asks what's the maximum weight. We know the maximum weight is when X equals to L. When the rope is completely folded onto the scale, the normal force or the scale number is the largest, and that will be 3 mg. So this is our final answer. Even though the mass of this rope is only m, but the number on the scale or the weight rated by the scale could be as large as 3 mg. After our discussion today, you should be able to find the momentum and the velocity related to continuous mass. What do we mean by continuous mass? You see, this rope, its mass on the scale is increasing continuously, and we used this change of momentum and impulse find the force related to continuous mass. And we also introduce another concept called linear density to find the change of mass for the continuous mass. Hopefully today's discussion helped you to know better about continuous mass and momentum. Thank you for your attention. I will see you next time.